Welcome back everyone. This is lecture 7 of our course on molecular spectroscopy. Up to this point, our discussion has been largely theoretical. We have explored quantum mechanical optical absorption, energy band structures, excitons and quasiparticles, and the mathematical framework of the Beer-Lambert's law. Today marks an important transition. We now move from theoretical physics to experimental physics. In science, understanding theory is only half the journey, and the other half is measurement. And measurement requires instruments. Our central question today is, how do we physically measure absorption? How does an abstract quantum transition become a numerical spectrum displayed on a computer screen? The answer lies in the architecture of the analytical spectrophotometer. Regardless of manufacturer, price or application, every spectrophotometer contains 5 fundamental components. Let us examine them carefully. First is a stable light source. This generates the incident radiation that interacts with the sample. Without a stable source, all measurements become meaningless. So, it is very important to have a stable light source. Second, a wavelength selector. This may be a prism, a diffraction grating, or optical filters. Its purpose is simple: to isolate specific photon energies or wavelength. Third one is the sample holder. Typically a cuvette, it must hold the analyte without introducing unwanted absorption. And the fourth one is detector, also called a radiation transducer. This converts photons into electrical signals. And the fifth one is signal processing and readout electronics. These systems amplify signals, remove noise, and finally generate the absorbance spectrum. Over the next few lectures, we will dissect each of these components in detail. Today, we begin with the most fundamental element, the light source. Let us move. For molecular absorption spectroscopy, we require a very special type of source, that is a continuum source. A continuum source is defined as one whose radiant power varies smoothly across a wide wavelength range. Why it is important? Because absorption measurement rely on comparison. We measure how intensity changes after passing through a sample. If the source intensity fluctuates sharply, we cannot distinguish. Is the dip caused by absorption or by source instability? Therefore, a smooth spectrum output is essential. On this side, you see irradiance plotted against wavelength. The vertical axis represents radiant power density, the horizontal axis represents wavelength. Notice the smooth curve. This stability forms the baseline for accurate spectroscopy. The upper graph corresponds to deuterium lamp. Observe carefully its intensity peaks. Deep in the ultraviolet region around 225 nanometers. However, its output decreases significantly toward longer wavelengths. Because of this limitation, commercial spectrometers automatically switch sources. Typically, below 350 nanometers deuterium lamp, above 350 nanometers tungsten lamp. This automatic switching ensures uniform intensity across the entire spectral range. Now let us understand the physics behind UV lamps. Deuterium and hydrogen lamps are the standard ultraviolet sources. They cover approximately 160 to 800 nanometers. Their operation is based on electrical excitation. An electrical arc passes through low pressure gas. This excitation breaks molecules apart. The molecules dissociate into individual atoms. During dissociation, energy is released as photons. Because the atoms separate with different kinetic energies, the emitted photons span a continuous energy distribution. This produces a smooth UV continuum, typically strong between 190 and 400 nanometers. Now, an important practical question, that is, why do we prefer deuterium over hydrogen? There are three main reasons. First one is higher brightness, second is larger emission region, and third is longer operational lifetime. Above 400 nanometers, sharp emission lines begin appearing. These are no longer ideal continuum. However, modern instruments can mathematically subtract these artifacts. Another extremely important detail is that the lamp window material. Generally, ordinary glass absorbs ultraviolet radiation below 350 nanometers. Therefore, glass cannot be used. Instead of that, we use high quality quartz. Quartz remains transparent down to about 190 nanometers. This material property sets the practical lower wavelength limit of most of UV visible spectrometers. Always remember, instrument performance is often limited by material science. Now, let us move into visible region. For visible and near infrared wavelengths, we use tungsten filament lamps. These are refined versions of incandescent bulbs, but engineered for scientific precision. They provide a smooth continuum from roughly 350 nanometers to about 2500 nanometers. The physics governing their emission is described by blackbody radiation. A heated object emits electromagnetic radiation according to temperature. This behavior was mathematically described by Max Planck through Planck's radiation law. The tungsten filament is heated to extremely high temperatures. As temperature rises, the radiation intensity increases and shifts towards shorter wavelengths. The peak emission lies in the infrared region around 1200 nanometers. Because emission depends on temperature, output intensity depends strongly on applied voltage. Therefore, spectrometers require highly regulated power supplies. Even small voltage fluctuations produce measurement errors. Modern instruments are using tungsten halogen lamps. A small amount of iodine gas is added inside the quartz envelope. This enables regeneration cycle. Evaporated tungsten atoms recombine chemically and redeposit onto the filament. This prevents filament thinning and allows operation near 3500 Kelvin. The benefits include high efficiency, longer lifespan, and extended spectral coverage. Notice from the graph, as the intensity drops sharply below 350 nanometers, which explains perfectly why the deuterium lamp is required for UV measurement. Together, deuterium and tungsten form a complementary system. Now let us examine what are the modern alternatives available, which includes LEDs and xenon lamps. Advances in solid state physics have introduced new light sources. The first is light emitting diode or LED. Unlike continuum sources, LEDs are semi-monochromatic. They emit relatively narrow wavelength band, typically 20 to 50 nanometers wide at half maximum intensity. Their emission wavelength depends entirely on semiconductor composition. For example, gallium nitride produces blue light. LED has various advantages which includes long lifetime, low power consumption, mechanical robustness, environmental friendliness. White LEDs operate differently. They combine a blue LED plus a phosphor coating. The phosphor converts part of the emission into longer wavelengths, producing a broad spectrum from roughly 400 to 800 nanometers. These are increasingly used in portable spectrometers. Finally, we consider xenon arc lamps. These are extremely powerful sources. They produce a strong continuum from 200 to 1000 nanometers. Peak intensity occurs near 500 nanometers. Because they consume large power and generate intense heat, they are often operated in pulse mode. Capacitor discharges create short, high brightness flashes. This achieves high intensity without overheating the system. Xenon lamps are especially useful in fluorescence spectroscopy and fast time resolved measurements. So today we have transitioned from theory to instrumentation. We learned that every spectrophotometer contains 5 essential components. We then explored the physics of light sources, deuterium lamps for ultraviolet region, tungsten lamp for visible and infrared region, LEDs for compact systems, and xenon arc lamps for high intensity applications. In the next lecture, we will study the wavelength selector, the monochromator, and understand how instruments isolate individual photon energies. Thank you.